In 2001, water authorities in Washington, D.C. needed to comply with new federal regulations targeting disinfection byproducts. To meet these updated standards, they changed their secondary disinfectant from free chlorine to chloramine. Almost immediately, heavy metals began leaching from the city's older pipes, causing a massive, localized spike of lead in residential tap water. It took an independent engineering investigation outside of standard regulatory channels to expose the true data and force a government response. The ensuing crisis stemmed from a severe miscalculation of distribution chemistry. We tend to think of municipal water distribution as a passive delivery network, a static series of inert pipes. But in reality, a modern city's underground distribution grid actually operates as a live, thermodynamically delicate chemical reactor. The failures in Washington, D.C. were driven by an inability to account for the electrochemistry inside that reactor. To understand exactly what went wrong, we have to track three hidden variables interacting underground: chloramine speciation, nitrification, and oxidation-reduction potential. The process of chloramation involves the intentional addition of ammonia to free aqueous chlorine to create inorganic chloramines. This equation shows the stoichiometry required to produce the molecule utilities want, monochloramine. This requires specific constraints: a chlorine to ammonia weight ratio between 4.5 and 5 to 1, at a pH above 8.0. Exceeding a 5 to 1 ratio thermodynamically destabilizes the solution, forming dichloramine. Once dichloramine forms in the distribution system, it degrades rapidly and generates severe taste and odor complaints from consumers. Pushing the ratio even higher triggers the formation of trichloramine, a highly volatile compound that easily gasses out of the water entirely. Generating an effective secondary disinfectant is a highly sensitive stoichiometric balancing act. To navigate this precise balancing act, water utilities use a strict operational boundary called the breakpoint chlorination curve. This graph maps total chlorine against the precise chlorine to ammonia weight ratio. The curve's peak is the ideal zone, where monochloramine reaches its maximum and free ammonia hits zero. Moving further right, the concentration line plummets into a dangerous dip. In this zone, excess chlorine triggers rapid decomposition reactions, actively destroying the chloramine residual you just created. Pushing past this breakpoint leaves only highly reactive free chlorine remaining in the system. Utilities must tightly control their ammonia and chlorine inputs to avoid crossing this breakpoint line and instantly losing all microbial protection in the pipes. Inside the physical pipes, maintaining that chemical balance confronts the first major distribution vulnerability: nitrification. Utilities use monochloramine specifically because its lower reactivity allows it to penetrate bacterial biofilms much deeper than free chlorine. The flaw in this design appears over time. As monochloramine naturally decays, it releases free ammonia directly into the bulk water. That free ammonia acts as an ideal nutrient source for ammonia-oxidizing bacteria living within the pipe biofilm. As these bacteria consume the ammonia, they excrete nitrites and hydrogen ions back into the surrounding water. The rapid accumulation of those hydrogen ions causes the localized pH of the water to drop significantly. This creates a thermodynamic feedback loop. The lowered pH accelerates further chloramine decay, which in turn releases even more ammonia. The primary disinfectant inadvertently acts as a biological catalyst, feeding the very biofilm it was designed to destroy. That localized drop in pH directly feeds into the second vulnerability and the direct mechanical cause of the DC water crisis: scale destabilization. Water systems rely on oxidation-reduction potential, or ORP. For decades, the free chlorine used in DC acted as a powerful oxidant. High ORP created a stable passivation layer of lead-4 oxide inside the city's old pipes. The 2001 switch to chloramine lowered this oxidizing potential. Without a strong oxidant, that solid scale became thermodynamically unstable, chemically reducing into lead-2, a highly soluble state. This newly soluble lead dissolved directly into the drinking water supply, heading straight to residential taps. By solving a regulatory issue with a weaker oxidant, the utility unknowingly stripped away decades of essential chemical passivation. This map shows how the impact of microscopic pipe chemistry scales across an entire municipal city grid. Water leaving the central treatment plant can be perfectly balanced, hitting the optimal 4.5 to 1 ratio and a highly alkaline pH. But at a mid-city node where the water age has increased, the nitrification cascade triggers, dropping the pH. Out at a dead-end pipe, the ORP completely collapses, causing active, severe lead leaching. A single standardized chemical input inevitably creates highly varied, hazardous electrochemical zones throughout a complex network. The DC water crisis exposes a harsh reality. Widespread chemical failures are a thermodynamic inevitability when distribution equilibrium is ignored. Water quality cannot be evaluated strictly at the treatment plant output. Modern utilities must actively manage stoichiometric ratios, temperature, and electrochemical equilibrium, all the way to the very last tap. The distribution system remains an active, volatile, and highly sensitive environment. True infrastructure safety requires balancing the exact thermodynamics of chemistry against the unpredictability of biology.